showing up for this last day of the conference. I mean, I don't know, maybe because of the train strike you didn't have a choice, but yes, thank you. Thank you, of course, to the organizers for inviting me to the whole program, to give a talk at this particular winter school. Yeah, it's early and the subject is probably not that familiar to most of you, so I am talking on the blackboard to force myself to go slowly. And so, like, if you don't understand anything because I'm going too fast or because I'm not defining things clearly enough, please just stop me at any time. It's fine, the talk is modular, there are plenty of, things which can be expanded or contracted as necessary. Yeah, so the main object of study is very simple to define. We have K, closed convex set in Rn. I'm completely incapable of drawing convex sets without making at least one error of non-convexity. It's called K. PK, the projection onto K. This is always the Euclidean norm. I'm mentioning this because there will be another norm which is annoyingly related to this. But this is the Euclidean norm. Okay, y. Something like this, pk of y. And, okay, this is a function we understand. Now, fix. Okay, this is maybe the first thing which is weird. Why am I suddenly denoting points by f star? And let C be a standard Gaussian. Let C be a standard Gaussian, and let y equals f star plus c, fn hat equals pk y. Okay. Okay, so we fix a point f star.
Really?
Yeah.
Remove the...
Sure. We fix a point f star in, this is too much for me. We fix a point f star somewhere in our body. We add standard Gaussian noise to it. F star plus DC. We project it back onto our body. We call this, again, with the strange notation, fn hat. And this is a random variable. It depends, it's a random variable, it's a function of c for f star fixed. We'd like to understand things such as how close is it to f star, what's its expectation, its variance, things like this. We can ask this about like any other random vector. The only question is why am I?
Why?
Yes, and why the weird notations? That should already tell you that something is going on.
I think the picture is a little bit misleading because, the projection of f n plus whatever c is not on the same line segment.
Yeah, not necessarily. It has,
Yes.
a priori it has nothing to do with. Let's put it here. So this is this, and this is this. Yeah, thank you, Preston. Yeah, if it were just always radial shrinking, things would be a lot easier, but if it's not. So like, what is this object? Why am I denoting all kinds of things by f in places, and why am I using weird terms like admissibility and empirical risk minimization? So the answer is because this is a problem which comes from statistics. And what does one do in at least non-parametric statistics? In non-parametric statistics, you have some kind of domain, class of functions f, some domain to R usually. And you're given observation points, x1, xn in the domain, and you sample the function at these observation points, except you don't get clean samples, you get noisy samples. Star. F star 1, F star of xn plus cn, yn, y1, etc. And like usually one assumes that the noise at least is IID. Usually you even take it to be standard Gaussian, at least in like these like real valued settings. You also have settings where the image is not R, but say just Boolean, right? Classification problems, and then the noise looks different. But this is a very, it's very generic and covers a lot of problems. And yeah, and the goal is, given x1, y1, xn, yn, recover star as closely as possible.
Oh, sorry, another question. So can it also happen that f star plus c is inside k?
Yeah, of course. In standard Gaussian, anything can happen. You can also happen like not to get noise. Could be a star.
Mapped onto the cell.
Yeah, I mean it happens with probability 0, but
Okay.
yeah.
We should treat K as a significant interior.
Maybe not.
Why it happens if probability is zero? Why is probability zero?
Oh, like if you take a vector in Rn and add a standard Gaussian to it, then the likelihood that
Well, it depends on k. If k is huge, I tend to
Yeah,
get
but before-
I don't see why if you add Gaussian vector, it will be outside.
Oh no, I was just saying that like the probability that you'll land on f star on the nose, meaning that there will be no noise, is probability 0. That's all. No, the probability that you stay inside k is some probability, but this is not necessarily helpful. If you stay inside k but are far away from f star, then this is not good, right? Our goal is again to recover f star. This is already like you may be realizing how this is somehow connected, and you'll realize that landing on a point over here is not helpful from this perspective. Yeah, so what is as closely as possible? So I mean you have to give some kind of error metric. I actually didn't write it this way, but yeah, like yeah, I'm just going to write it very generically and leave things not entirely formally defined.
Eli,
What?
very sorry. So if it doesn't matter that if you land in K but at a different point it doesn't help you, could you then optimize over different K?
Like usually this thing is given, right? Like think of f as whatever the class of well, time for our first example. N. linear regression, right? You have a bunch of points, you want to draw a line through them. F here is the class of linear or affine functions or whatever. And this is given, right? You're not going to change K. I mean, you are. I mean, this is part of the question of model selection is a huge question, of course. But like we're staying within one, for the purposes of this talk at least, we're staying within one specific model and then saying, you know, all we can possibly say about this model. And, you know, downstream, once you can use that information, you know, whatever you know about how well this model performs to decide between this and other models, certainly. But for the purposes of this, we're staying within one model, as in, i.e., one function class. Yeah. Okay, now that I've said linear regression, I should also say something about this recover f star as closely as possible. So we have some kind of loss function, which usually is of the form, usually it's of the form f minus g phi of f minus g d mu, where phi is some function, phi is some convex function, phi of 0 equals 0, d mu is some measure. In the case of linear regression, what one is trying to, what usually one is trying to do is, like the standard method for linear regression is least squares, right? So, argument over beta in RD, beta 0 in R, sum I equals 1 to n, yi minus beta x plus beta naught squared. Did I write that correctly? Hopefully. This is, you know, least squares. Maybe you've seen this somewhere at some point.
Can you explain what is K in this picture?
So in this case, K is, well, I've written K actually. I've written K. K is, well, in this picture it's R2, yeah. Or, you know, I wrote this.
What do you mean closest point in R2?
So that's
you define projection using some points body, it should be bounded.
no, well, K, I mean, K is RD plus 1. But note that the image space is Rn, right? So K is RD plus 1, which is somehow embedded in Rn. It's linearly embedded by this map, actually. And essentially what is going on is that you're projecting orthogonally from Rn to RD plus 1. I haven't written it in this form, but...
so K is part of this line there?
It runs in a completely different space than this. I'll get to it actually a bit later. Right now I'm still like talking about basic notions in statistics and not yet going back there. Yeah. Okay. Whoa. This is really heavy. What am I doing? I have no idea what I'm doing. I want to write on the top of the board, but I also don't want to press it onto the board saying.
Where's the other one high?
Yeah. Okay. Okay. Hopefully that's good. Yeah. So that's linear regression. A bit more about, let's just define risk and min-max risk, and then come back to these notions later. Okay, so we have a loss function. We have a loss function L, and we have, okay, so F, L loss function. And what's an estimator? Well, an estimator is a procedure, or you can think about it as a function. Possibly, like, depending on the number of samples, which sends your observation points, yn to, well, yeah, this is an abusive notation, but the f bar n in f. This is what's called a proper estimator, because maybe in some situations you want to return a function which doesn't lie in your original class, but for our purposes, we're only considering proper estimators. And we given an estimator the risk. Risk is defined as r then x star is the expectation of loss. Very simple. Meaning, okay, implicitly this expectation is over the noise, right? For every value of the noise, you get some data. You get x1 through xn through yn, right? Now, if your original function was this line, then for every value of the noise, you get some stuff lying close or far away from this line, and you get some least squares, which is not going to be the original line. And so the loss function measures how close you are. The expected loss function is the risk. That's all. Min-max risk is the risk of the best possible estimator with respect to, well, this min-max measure. Min fn hat, max f star in f of the risk fn hat f star. Meaning this internal thing, right, is the worst possible, the place where the function for which our estimator performs the worst possible. We'd like to find the estimator which has the best possible worst case performance. That's the min-max risk. It might not be like always the measure you want to look at, but in classical statistics where you're not assuming anything about the distribution of functions from your domain, then somehow you can't do any better because you have to work adversarially and like assume that people are choosing them, the functions as badly as possible, because again, you're not starting with a distribution over functions, so you have to perform as well as possible on all functions. So that's why like the min-max risk is the most classical measure. Okay, time for another example of an estimator, another extremely classical example, but this time phrased very generically. Well, given data points, no, I mean, we have data points, and we'd like to answer the question, what is the most likely f star from which they came? So we can't answer that question if we don't have prior distribution on functions. We can answer the opposite question, right? Given f star, how likely are we to see these points? So this if yn, if we have yi equals f star of xi plus xi plus Gaussian noise, then we have p yi given f star is just x minus 1/2 yi minus f of xi. Let's just proportion f of xi squared, right? This is the likelihood of seeing each individual yi. Just, density of the Gaussian between where you started and where you end up. So the likelihood of py given f star is proportional to x of minus 1/2 the sum yi minus f of xi squared. we want to maximum likelihood say, this is called the likelihood. The likelihood is a function of f star, which tells you how likely are you to see your observation points given that the true function was f star. So this is the likelihood in the case of IID, standard Gaussian noise. And the maximum likelihood estimator says, let's maximize the likelihood. And in the case of standard Gaussian noise, that means the same as minimizing the sum. So for standard Gaussian noise, then the maximum likelihood estimator is just the least squares estimator. And yeah, which I wrote down there in the case of linear regression. And one other thing to note, I mean, this thing is called, it's also called the empirical risk minimizer. Yeah, why is this called the empirical risk minimizer? Well, this is already like getting into a setting that I am like not going to talk about. I basically have bracketed thus far the question of where the xi are coming from, right? But you can imagine two different settings. Either the xi are fixed, fixed points once and for all. I always sample, say, my linear function at 1 over n, 2 over n, blah, blah, blah. Or my xi are drawn randomly from the distribution. Again, you can complicate the model as much as you want, but somehow the standard way of thinking about it is that you have some prior distribution. Say if your domain is some subset of Rn, and like the uniform distribution on the subset of Rn, and then you get your xi from this distribution, right? You don't get to choose your xi. And then your risk metric, the natural risk metric, is how well you perform on the whole space, right? And then like mu is how well, mu is the same distribution you sample points from. So this is called the population risk when mu is some density on the whole population, which doesn't just take into account your performance at the points you've sampled. But this kind of expression is called the empirical risk because it looks at the points, well, empirical, experimental, right? Is the points you actually sampled and tries to minimize some function which depends only on the points you've actually sampled. You can also think of this as a population risk with respect to, the uniform measure on the sample points. And this is called the empirical measure. N equals N sum delta X. So this is why it's called empirical risk minimization, because you're minimizing a risk function which uses this measure rather than a measure which is on the whole population. But that was just in brackets because we are now going to only talk about the setting where the xi are fixed. We have results when the xi are not fixed, but it's much more complicated and requires introducing many more notions in statistics. So I'm just going to talk about the fixed setting. Are we on time? Okay. Yeah. So now I want to convince you that if the xi are just fixed points, and we look at the maximum likelihood estimator or the empirical risk minimizer, which is basically the same thing, then I've reduced to my first problem, which I've conveniently left on the board. Yeah. So let's just say f is compact convex in some reasonable function space. If f is compact convex in a reasonable function space, and well, the evaluation map is continuous. That's what reasonable function space means in this context. But then
It's compact convex with respect to what topology?
Exactly. With respect to any topology such that, well, it's sufficient that the evaluation functional at any point is continuous. But the whole point is to like get rid of this. This is just motivation. X, F and F. So is compact convex. Meaning if F is nice enough, and think of an example like Lifshitz functions on 0, 1. Then the set of like possible like evaluations on your n sample points is also going to be compact convex. And then the empirical risk minimizer is, given y equals x star x1 f star xn plus c. The goal is to find f such that this is minimal, but that's the same as to find a point in Fn which is close to this.
So these points are all in Rn, right?
Yeah.
F of x1 up to f of xn is in Rn. And
Yeah.
But you say that curly f is a compact.
Curly f is some subset of the set of measurable functions on the domain, which is going to be convex in a reasonable topology.
But then you say that this subset in Rn is supposed to be compact, right?
Yeah, this is the this implies this. Again, like
okay.
yeah. I'll give an example to like clarify what's going on very shortly. So yeah, under this, So then what I claim that in this situation our model reduces to the thing I put up there, right? So what's going on? We're drawing our we have a vector of observations, which is like the vector coming from the vector of function evaluations plus Gaussian noise, right? This is what we're given. And we want to do empirical risk. Can everyone see this? We want to do empirical risk minimization as in minimize the sum, right? Like find the f such that this sum is minimal. But this is just the distance between y and f in the Euclidean metric on Rn. So this is the same as finding the closest point in the set Fn to y. So if I just rename Fn as k, that's precisely this. Is this clear to everyone? I see a lot of nods. I don't see anyone shaking their heads, but I do see people who are doing neither. So that is the situation. We'll just give one example for just concreteness. Example, f f 0, 1 to R. F has to be bounded for compactness, certainly, and F is 1 Lifshitz. One bounded 1 Lifshitz functions, and on the interval, and take x1 to xn. Might as well take them to be ordered on this interval. On the interval 0, 1, and a function is going to be bounded Lifshitz if and only if the distances between adjacent, it only has to satisfy the distances between adjacent points are less than the distances, right? So Fn is y in Rn such that yi less than or equal to 1, yi plus 1 minus yi is less than or equal to xi plus 1 minus xi. Right? Just a convex set in Rn. And what happens in general? In general, right, you have some reasonably nice function, but you're adding Gaussian noise, right? You're adding, all of a sudden you have some point here, some point here, some point here, some point here, and you can't even and you can't even connect these to form a one-Lifshitz function. So the projection is going to do something non-trivial, but it's probably not going to give you back your original function. So this is a very classical example, very well understood. Exercise for those for whom I'm going too slow. What is Fn in the case where you do everything in some domain in Rd, where you don't have this natural order? So maybe it's less obvious what possible function evaluations can happen if you force your function to be one-Lifshitz. Okay. Blah 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 blah. Okay. I have spoken for 30 minutes. Excellent. That means I get to skip something that I was planning on talking about if I had too much time. Oh yes, we don't do this in this country. If it wasn't obvious, I have no idea what I'm doing. Okay, so now we've reduced to our, I don't even know how to put this down. Okay. So now we've reduced to this problem. And, I erased the definition of minimax risk, right? That's kind of important. Let me write that up here. Oh. In Fn bar, sup f star in K, Fn bar minus f star, expectation, squared. And now you'll notice that I've written two bars here, and I've written n downstairs, and the reason is because I am going to be defining this thing as 1 over square root of n times the Euclidean norm. Why am I doing this? For a very simple reason. This is the distance, but it's somehow the normalized distance, meaning we think in statistics about a context in which we get more and more samples from a distribution, and we expect the error to decrease as we get more samples. So so if we measure the risk with respect to this empirical measure, the empirical measure is a probability measure. So the risk here is actually going to be 1 over n times the square root of fxi minus yx squared, right? If you just compute this. So you want this 1 over n here, like that's somehow natural, otherwise your risk would just increase as you get more and more samples, which doesn't make sense. So this is somehow the natural measure to use. And so I'm writing the minimax risk like this. And
so Fn bar is Fn hat bar.
No. This is the infimum over all estimators. And this is precisely This is precisely what's interesting about this whole story, which is that Fn hat may not be a minimax optimal estimator. It may not be a minimax optimal estimator up to universal constants. It's unfortunate because the ERM is something we can usually compute if K is some nice polytope. It's something we can give to a computer to compute in polynomial time the projection onto a convex set with a reasonable number of facets. Such as, did I erase the Lipschitz example? Right, but in the Lipschitz example you have polynomially many facets, so it's not a problem. The difficulty is that it's known what estimator attains the min-max risk here, and basically what you do is take a net in your convex set and return the point in the net, take a net of appropriate size, and return the point in the net which is closest to your to the vector you're given. And this is very simple to state, but it is not really computable. I mean, it's computable in exponential time because sets in Rn tend to be of size exponential in it. So that is basically the issue we're dealing with. That we have this notion of minimax optimality, and we know that for the BERM is a very nice estimator, and it's very we'd like to use it, but we know that it's sometimes bad. So this is the context in which.
I'm sorry.
Yeah.
So what is Fn bar?
This is any estimator, right? The min-max risk is the infimum over all possible estimators, which are all functions from Rn to Rn, basically, or Rn to K, if you want proper estimators.
All functions.
Yeah. Yeah, all functions, all computable functions in some vague undefined sense. Yeah. So as it turns out, like theorem, the min-max risk this is not our theorem. To epsilon star squared, where epsilon star solves the equation what have I written down here? So I heartily encourage all of you to ignore this local. This is the local entropy, which is something, some property of the convex body K, but just think of it as the entropy. Just the entropy of K with respect to, with respect to the size epsilon, as in n K epsilon covering number of K eyeballs over base epsilon. And local of K is something similar to this, but more complicated. It's always bounded above by it. Under nice enough assumptions, it's the same. So
which norm are you using in this case? Which norm are you using?
I'm using that norm. I'm using that norm to measure the risk again. But I'm still using the original norm on the domain space. Meaning I'm using the original norm here, but using the 1/squared of n scaled norm in epsilon star.
You cover by Euclidean balls, right?
Yes.
Okay.
Yeah. So this is like somehow what I was saying before, that what you're supposed to do, right? What we know is minimax optimal is to take a net of the appropriate size and return the point closest to the net. So we expect that the size of the net is what's going to show up here, what's going to show up in the definition, right? Notice that there's only one solution, right? As epsilon increases, this thing increases, this thing decreases. So, they cross somewhere.
Ellie, I have
Yeah.
a really silly question. How is this related to the entropy that I know, which is like of a function, like minus integral f of x?
I'm not sure, but like the entropy. I mean, this is also the entropy of the functional entropy of a uniform prior on this net. That's all I have.
That's awesome.
Yeah, that's all I'm going to say at this time because I'm running even later than I planned to run. Yeah. So this is and the ERM does not attain this. Does not attain this risk. But we, to state our result, I am going to just remind everyone of something they should know, which is the bias variance decomposition, which is that if you have no, this is somehow very general. Squared plus squared. Okay. Yeah, I mean this is true. I mean I wrote this for our specific case, but
Are there some bars missing?
where would there be bars missing? Yeah. Oh, there are bars missing. Yes. Sorry. There are bars missing. Yeah. This is bias variance. This it's like a Pythagorean theorem, and they.
What is this? Why is
Let's say I have a random function f and a fixed function g. F minus ef. I'm not going to prove it. It follows very simply from some orthogonality. But basically the error. This is the error, right? This is the. This is what we want to control. So the error of an estimator. This doesn't depend on this being the empirical risk minimizer. It's true for any like random function. The error of the empirical risk minimizer is you can decompose it into two things. One is how much it changes within itself. This is just the variance. This is by definition the variance. And one is like how far is it on average? Meaning you have this average. This is not no longer random, right? This is the expected ERM, and the distance between that and f star. That's called the bias. So, you could have an estimator with zero variance, which is bias, like, always pick a fixed point in K, no matter what your observations are. That's how you minimize this. You could try to have an estimator with low bias, but then, you'll probably end up getting high variance. Obviously, we would prefer that both of these were as low as possible. Yeah, so our theorem, which I'm not going to have time to prove, even though the proof is beautiful and not too long, but I still won't have time, is that the variance is always minimax optimal. This is true as in, if the ERM is bad, it's because it has high bias, because it never varies too much from its expectation. The proof, by the way, it's very nice. It's not my proof. The proof is that fn hat is a one Lifshitz function of the noise, and so we have Gaussian concentration for this one Lifshitz function. So that's what, and you want to you want to balance two sort of error probabilities, and this turns out to be exactly the balancing which happens. I don't have time to say more than that. But yeah, so this is somehow something very simple to state about ERN that was overlooked before. We have a result. Oh, and because this thing is doesn't really use any specific properties of Fn hat, then it's true for any one Lifshitz function. Any one Lifshitz function from Rn to Rn or whatever. You put it here, then its variance is going to be to solve this equation, or to be bounded by a universal constant times this.
Yes, what does it mean asymptotic to epsilon stars?
There is a universal constant such that there are universal constants, C and C, such that if epsilon star is this, then the minimax risk is always going to be between what?
You can bounce from above and from below.
Yeah.
Like Cosmo.
Yeah. Independent of k, independent of everything. Yeah. Sometimes instead of saying that the minimax risk is asymptotic to this, they say that the minimax risk is the solution to this, and that makes even less sense. So I tried to write it in a more rigorous way. Yeah. So the variance is bounded by c times this epsilon star squared for universal c. There is a consequence of this which I can prove. So we'd like to have an estimator which is the best possible over all functions, but sometimes that's hard. So we at least would require that our estimator is admissible. What means that an estimator is admissible is simply that there's no estimator which outperforms it on all functions. So for instance, the estimator which no matter what values it gets, it always returns a fixed point in k, it's admissible because it does the best possible if your unknown function was that original point. So admissibility is not necessarily, just because an estimator is admissible, it doesn't mean it's good. There's a famous theorem of Stein, the same Stein, which says that the least squares estimator for mean estimation on Rn is not admissible. Meaning, if k were Rn and you did this thing, then no, hold on. Yeah. If k is Rn and your goal is to return an estimator of your point, given that point plus noise, well, the empirical risk minimizer is obviously just return that point, right? And this is not admissible. This is a famous result of Stein. So admissibility is weird. What is local? Not local, weak admissibility. So we have a result, as a corollary of this, we have a result which says that the RM is admissible. This is a reproof, like a much simpler reproof of a theorem of Chatterjee. I'm not going to prove that. I'm going to prove something weaker, which just says that there exists f star in k such that error on f star, which I'm not going to even write, is less than or equal to c epsilon star squared. This isn't admissibility because it could be that there's an optimal estimator, that the error on f star is much less than the minimax rate, right? The minimax rate doesn't preclude there being there being functions for which the error is much smaller. But all we're saying here is that the error on f star is less than the minimax rate for the ERN. So this I can prove to you in half a line. And look at this. We have the bias variance decomposition. we said that this was bounded above by a constant times the minimax rate, so we have to just bound this for one f star. So now just know that the function f star to the expected the expectation, right? The expectation of the empirical risk minimizer. This is a continuous function from k to itself. By Barrow's fixed point theorem, it has a fixed point. For that fixed point, this is 0, and that's the proof. Yeah. Another theorem, which I'm not even going to state, gives us a lower bound. No, I am going to say this. V of fn exists f star, v of fn greater than or equal to epsilon to the 4th. So this is a partial converse to this, but it's not that. That's the open problem. The open problem is to get a lower bound which is of the same order as the upper bound. Yeah, so I've done what I wanted to do, which is state an open problem, and I can finish now and open 2 questions.